Hello chemistry students, this is part of a series on the separation of mixtures. In this video what we're going to do is we're going to take a look at the separation of solids. And by this we mean finely divided solids in most cases, such as mixtures of powders. And the first technique we're going to take a look at of several is sieving. And this is a pretty simple technique that relies on differences in particle size. And so this can actually mean that you're using a sieve to actually separate different particles of the same material, or different materials that are actually of different particle size as part of a mixture. And shown here is a picture of a sieve that is commonly used in a laboratory to separate a mineral, for example. Sometimes to help this process when you're separating particles, you may, for example, use some water to actually make your particles easily flow through the sieve. The little holes in the sieve are known as the gauge, and what the size of the hole will determine the size of the particle that will actually go through the sieve. And what actually happens when you're sieving is you place your mixture on top of the sieve, you gently shake it to agitate and let small particles fall through, and they will be collected underneath the sieve, often in a tray. And you will retain any larger particles, which can at times be referred to as gravel, on top of the sieve. Now, in a lot of cases, it is possible to actually stack multiple sieves on top of themselves to actually get a graded set of samples separated from a larger mixture, and that can let you have a look at the proportion of particles in that mixture of different sizes, which is very, very useful from an engineering perspective. Okay, but the take-home point is the large particles are retained on top of the sieve and the fine particles go through. Okay, let's have a look at our next technique. Sedimentation is used when we want to actually separate out a mixture that contains particles of different density. And so this is actually a pretty old technique that is used in cases such as gold panning historically. Alright, and what actually happens is that you have a tray, and in that tray you have your particle mixture, and what you do is, with a little bit of water just to help it flow, is you gently agitate that tray, and what will happen is dense particles will be retained at the bottom of the tray, and often these trays will have little ridges just to help catch them up at the bottom of the tray. And then you can pour the liquid and the less dense particles by a simple process of decanting them off the top. And so that lets you concentrate and collect your more dense particles, and that's useful to gold miners, given that gold is really quite dense compared to the other minerals that it is found with. Alright, and this basic setup is actually applied still to today, using essentially a mechanical version of this known as a jig, which essentially is just what it sounds, a large mechanical vibrating pan that actually separates materials on the basis of density. Alrighty, that's really all there is to it when it comes to sedimentation. Let's have a look at our next technique. Our next separation technique is actually quite a fancy one, and it is known as magnetic separation. Now, what magnetic separation actually does is it takes advantage of the response of particulate materials to a magnetic field. And so if you have a material such as iron oxide, it will actually respond and be deflected in a magnetic field, which lets you manipulate it if it is part of a mixture of particles that are not all iron oxide. Maybe you have some quartz mixed in there, and that'll let you actually separate the two. And this is a process that is actually used to separate magnetite and other iron oxides from quartz and other impurities industrially, and has been used extensively since the 1960s to do so. Now, the basic setup of this is to have some sort of belt system that runs over a magnetic drum. And your mixture will run along that, and it will actually separate the non-magnetic particles, which will be unaffected by the magnet, and they will simply fall off the belt on the basis of their momentum and gravity. And your magnet will actually cause your magnetic particles to be retained for a longer amount of time on the surface of the drum. And then it's really just as simple as having a scraper to remove the particles from the belt as it passes along the drum, to actually scrape off the magnetic particles that are held onto the belt by the magnet, and essentially a physical wall known as a splitter, that is simply a physical divider that is used to separate the two streams of particles, so you can control the grade of what you're actually separating. It's a really elegant and simple technique, and it's from this magnetic separation that our next technique was actually developed, and that is electrical separation. And this actually relies on a number of physical properties depending on the exact nature of how you're separating the dry mixture of particles. Okay, and what this actually involves is, for example, you can separate a mixture of particles if there's a difference in conductivity. You can do it if there's a difference in resistance of the actual particulate materials. And of course, if you have materials that charge differently on the basis of friction charging, you can also separate this. And pictured just here is an example of a separator that works on the basis of frictional charging. And so what actually happens is particles pass into a vibrating bin just here, and that causes them to frictionally charge. And if you have a mixture of two different types of particles, what will actually happen is one of those particles will become positively charged and one of those particles will become negatively charged if they have a difference in the surface of those particles, a significant difference in the surface and the ability of those surfaces to lose electrons from the surface of the materials. And as it passes down into the separator, a common design is to actually have a rotating drum electrode which the particles pass onto, and above that having a second electrode. And what happens is that your negative particles, negatively charged particles, as they pass down here, will be deflected towards the positive electrode over this way, while your positive particles will be held onto the negative drum. And depending on how charged they are, they will actually drop off the drum at different points. And if they're really charged and they're retained on the drum, you can have a scraper similar to the magnetic separator to remove them from the drum. And again, you use processes such as a splitter as a physical wall to actually separate your particles, and you can shift them to control the actual grade. It very much is very similar to a magnetic separator. The only difference is you're actually taking advantage of the different electrical properties of the particulate matter that you're separating. And so this is just another way of separating a mixture of solids that is small particles that have different properties and different physical properties. That's all it really comes down to. Okay, let's take a look at our final technique, froth flotation. Froth flotation actually relies on an interesting physical property of divided solids and powders, that is known as wettability, and that is whether or not the particles actually like water or they don't like water. And so in terms of an actual process that relies on differences in physical properties, this is perhaps one of the separation techniques that it kind of skirts the line a little bit in terms of actually being a chemical property, because often what will happen is there will actually be some chemistry done to the particles to modify how they respond to the presence of water or to the presence of a bubble in terms of their attachment to a bubble by adjusting their wettability. So just to note, this is a technique where it's not just separated via physical property. Often they actually adjust the surface of the particle matter, the solid mixture, the surface of the actual individual particles of the solid mixture, to actually change how they separate. And the basics of this mixture is pretty straightforward. You have your mixture or slurry of particles in water, and what you do is you feed that into a agitated tank, where you stir it up and you make sure that it's all really well agitated, and from the bottom of that tank you feed bubbles up into the tank. Now if you have particles as part of your mixture that do not like water, they will attach to those bubbles and be carried up into the froth at the top here, and that looks like this just here. Okay, and this is a picture of a sulfide salt such as galena that is actually being carried up into the froth. All right, and that's lead sulfide. Now, what happens then is that concentrated particle that is just the particle we want containing the metal that we're after is then actually just essentially skimmed off the surface via a launder to actually concentrate this material. Alright, and it's an incredibly efficient process that has actually really changed the mining industry. It's one of those separation techniques that over the last maybe 110 or so years has actually revolutionized the mining industry and resulted in the ability of mines to actually economically separate minerals from waste material known as gangue that previously would have been uneconomical using older techniques. And so one of the things, just to finish off, was I just wanted to show you, this is a diagram that shows you what the bubbles in the froth actually look like, and you have your small particles of your mixture actually loading onto the bottom of those bubbles as they come up to the top of the froth. And so as long as you can actually have one part of your solid mixture, one component selectively attached to those bubbles, you're able to concentrate your component that you're separating by having it attached to those bubbles selectively. And you may have to modify its surface. In the case of mineral sulfides such as galena, sphalerite, chalcopyrite, you can often actually use a xanthate, a class of molecules known as xanthates, to actually make the surface not like water and make it like the bubbles, and that actually results in it quite readily attaching to those bubbles. And it's as simple as actually then skimming or directing those bubbles down a launder to actually separate them off and concentrate your mineral. It's a really elegant system, and it's a really nice one to finish on. Alright, so that brings our series of videos on separation to a close. I do hope this has been useful. Alright, feel free to comment in any of the videos or ask questions, and I'll hopefully be able to get back to you and either provide you with extra information or address your question. Thank you for watching. Bye.